Hey students, let me try another video solution. It's a pretty significantly hard one. It's from your chapter 27 college physics book, but it's in the harder book. So it's volume 3, chapter 3, number 72. And I printed it up here, and the picture will become helpful here. But maybe the first thing I should say is you might want to look at example 27.7 in your college physics book. In that one, they do an interference, and it is close to this one, kind of, not nearly as hard. That one has a soap bubble. And so they kind of think of the thin film as all having a uniform thickness. And ours has a wedge to it. And so that's one of the things that we're going to have to give some thought beyond just, what the book directly said. And so this is where that, it's been a while since I said it, but this is where the principles of physics come into play. Physics is about knowing how to apply a few fundamental principles to explain a universe of phenomenon and the different colors. In fact, the different colors that would come out of the different thickness kind of remind me a little bit of although it was slightly different, that article I sent out about the translucent fish. But that aside, let's not worry about the difference between those. But I do want to point out how I'm going to attack this problem, because it is a notch up from, this example. So I'll say it again. This example problem had a soap bubble. And so there was air on the outside of the bubble and air on the inside of the bubble. And it talked about how the light would reflect off of the top surface and then the bottom surface. And these two beams, although it could have been argued that there'd be 3 beams and then 4 beams and 5 beams and an infinite number of beams. But it turns out that we really only have to study the first 2, because the conclusion we get from the first 2 matches the infinite number. And so that's kind of a fun set of mathematics in itself. I'm glad they're not asking us to do that tough of a calculation where we have to show that these other rays are the equivalent of the first 2. But in this derivation, just focusing on the first 2, the author said something like this: if the down and back, and I've kind of drawn it at a little bit of an angle, but your author is saying if you just go straight down and back, but I'm going to draw it at a little angle so I can see them, the distance traveled is twice the thickness. And then your author argues that if that is an integer number of wavelengths, and here's where you got to be careful, wavelengths in the soap, and so calling n the index of the thin film here, if that is an integer number of wavelengths, you might get constructive interference, but you might also get destructive. It kind of depends if anything else is happening. And if nothing else was happening, you would say it's an integer number of wavelengths, and that's our path difference. That's the whole topic of chapter 27 about treating light as waves and having constructive and destructive interference. And so if one goes a longer path than the other, and this is the longer path, twice the thickness, and if that's an integer number of wavelengths, and I should say wavelengths with, that extra distance it went, and the one that went into the soap actually went extra in the soap, so I'm talking about wavelengths in the soap. If that's an integer number of wavelengths, you expect to get maximums. And so if there's 1 wavelength or 2 wavelengths or 3 wavelengths, you expect to get constructive interference. And again, if nothing else were to happen. But as you read this example carefully, you will see, I'll change colors here, that they say you got to be a little bit careful when things reflect, because the reflection inverts the wave. In other words, a crest becomes a trough, or another way of saying that, it's equivalent of a half wavelength. So we should ask, are there any of these phase shifts? And we learned that there would be if you reflected off something of a higher density. So this first one, I'm going to put a circle around it to indicate there's going to be a phase shift that's the equivalent of a half wavelength. Then I'll just put lambda over 2. Because it's going from the air, which has an index of 1, into the soap, which is mostly water, a little bit other stuff, so I'll make it index a little bit higher than water. And so it would have an index probably about a 1.34 if I was guessing. The point is it's way above 1, and it's going to have a phase shift. But this first one has a phase shift, but look at the second one. It does not. It goes down, and then it reflects off of the air interface. So it's in the soap going into the air. And so I'll just put a little no here, no additional phase shift. So when a crest is hitting it, it'll come off as a crest. Or when a trough is hitting it, it'll come off as a trough. Okay, and then it goes down, and then it transmits through. And we never have a phase shift on transmission. I guess, we could have said that about coming in, the one that comes in and goes through the soap. We didn't talk about a phase shift there. We only talked about the percentage that was reflecting off. Because, again, that's a transmitted. So the stuff coming in gets transmitted, and the stuff coming out gets transmitted. So no phase shifts there. The only potential that it would have a phase shift for wave number 2 is at this boundary, but this boundary is a reflection from a high index to a low index, so none. Now, here's why that's important. Coming back to example, 27.7, I would say, okay, with nothing else going on, so with ignoring these phase shifts, I would have said that twice the thickness being an integer number of wavelengths would give me maximums. But now realizing that there is something more going on and realizing that one is getting an extra half wavelength and the other is not, instead of them lining up and getting you constructive interference, you would get destructive. Okay? And so this would be the appropriate equation to get destructive interference. And the other equation, which would correspond to the extra path difference, 2t, being an integer and a half wavelengths, which, again, ignoring phase shifts, you would have said, oh, that has destructive interference, that would be minimum. But then, because one undergoes a shift and one doesn't, it becomes a maximum. So just to kind of follow above, I would have said without any other phase shifts, this would be a minimum. But now that I've analyzed it and there is a phase shift, I would cross that out and say this is the equation. Of course, you don't really need to give much thought. You would just say, well, if this is the equation for minimums, then this would be the equation for maximums. Okay? Now, I hope I didn't talk too much about example 27.7, but I just wanted to do a review of our thinking and our logic in section, actually it is section 7 also, so not only example 7, but section 7 of 27 is where we talk about the thin film interference. So I'm going to use that information, but talk about this problem. So let me maybe put it like this so that I can then talk about, all right, what if instead of having a soap bubble, I have an air pocket. And to make it look like this one, see, we've got glass slide, which is some thick piece of glass up here, and underneath it, a glass slide. And so our thin film, like the soap bubble, is ray number 1, which is going from the glass into the air, and then so that's the reflected one. And the other ray, which transmits into the air, then bounces off the glass interface and transmits on up. Let me call that ray number 2. Now, if we kind of do the same logic and call this a thickness of T, kind of like we did back here, we might do something like this. We might say if 2T is an integer number of wavelengths, and let me say it again, wavelengths in the thin film, and so in this case it's air. Well, last case it was soap, but in this case in the air, if that extra path length, 2t equals an integer number of wavelengths, if nothing else happened, you would expect to get maximums. But there is, at least potentially, something else going on. And so just like I was kind of arguing here at the soap bubble, we have to ask ourselves, is there an extra phase shift in one of them or both of them due to the reflection? So let's talk. So the first one comes in as in glass, and the index of glasses are in the 1.5 range. And it's going into air, which has an index of a hair over 1. I'll just call it 1. I think 0003 would be a little more accurate. But the point is, it goes from high to low, and so I'm going to just put a little no here. There's no phase shift, and so unlike our earlier discussion, I'm not going to circle it. I'm not going to say there's an extra phase shift. I'm going to say no, there's nothing more to consider. So maybe this is going to become out to be a maximum. However, if you're looking forward on this, you will see that ray number 2 does have a phase shift because it's in air and bouncing off glass. And again, glass is about 1.5 and air is about 1. And so there's going to be a phase shift. So in this case, one undergoes a phase shift and the other does not. Now, it's the opposite compared to the soap, but that doesn't really matter which one went under the phase shift. If one of them does a phase shift, then where they used to line up crests lining up with crests, now the crest, let's say, of the first one is going to line up with a trough because this extra half wavelength equivalency. It's not an extra distance traveled, but what it's going to do is change the equation for maximums to minimums, and that means the other equation, 2t equals to m plus a half number of wavelengths in the thin film, is going to be the equation for maximums. So I would say that this problem with the air gap is a little different than the soap one, but yet the equations come out to be the same. And that's why I thought it would be best to kind of springboard off of example 7 instead of example 6. Because example 6, I can't remember, but either both of them had a phase shift or neither. I think it was both. But if both or neither, it ends up being the same equation because it's the difference between them. So, and when I say same equation, let me be careful. The same as it would if it were no phase shift. So this equation gives you maximums when you have either no phase shifts or both go a phase shift. And like I said, I think that's what's happening in number 6. But in number 7, only one of them undergoes a phase shift. And so the equation that was giving us maximum now gives us minimums. And the one that gives us minimum now gives us maximums. And so that's what happened in our soap bubble, but that's also what's going to happen in a little gap that is made out of air. And that's where I need to start this problem. There's still more to this problem, but that's my starting point to saying, okay, these are the appropriate equations for minimum and maximums. And now I need to go back here and when I read the problem, say, well, what am I looking at? Am I looking at minimums or maximums? So here it says a microscope slide is 10 centimeters long. So I'll just go 10 centimeters. Maybe you ought to put it along the slide, 10 centimeters. And it's separated by a very thin piece of separated from a glass plate at one end by a sheet of paper. So this is the thickness of the paper. Now let's call it D for a moment. I don't want to call it T because T is the thickness of the gap, and what makes this problem kind of hard is the thickness T changes. The gap changes because of this angle here. But at the far right-hand side, the gap is the same thickness D as the paper. But way over here on this end, the thickness is 0. And so the thickness varies. And we need to think about that for a little bit. That's what's going to make this problem hard. Okay. That is shown in the figure. Okay. The slide is illuminated from above with a sodium lamp. So that's kind of that yellow-orange sodium lamp. So we got the wavelength. And it has 14 fringes per centimeter are seen along the side. Okay, so when they're talking about fringes, I think they're, talking about the maximums. But sometimes people focus on the darks, the minimums. And in this case, I don't think it would really matter what our attention focuses on here. But nonetheless, we're going to look at, I'll use the equation in terms of the bright ones. Okay, but there's 14 fringes per centimeter. All right, so if you were to look maybe in a, I'll just go like right here, a 1 centimeter piece of the whole slide. And just focus on that 1 centimeter. And if you were to look down, you would see 14 bright dark patterns. And then it asks for what's the thickness of the piece of paper. Okay. So why don't we just do this? Why don't we say, okay, maybe you're looking at this edge right here. Okay? And that edge would have a certain thickness. Maybe I'll call it T1. And so if I were to apply this equation, I would say 2T1 equals some integer. Not real sure what that integer is. Plus a half. And then the number of the wavelengths in that gap. And in that gap, n equals 1. Okay, so this would be the wavelength, 589 nanometers. And for completeness, I'll divide by 1. Now, if I were to apply that same equation over here, I guess I would have 2 times a different thickness, T2. And it would be a different number of integers. However, here's the key. There's 14 of them, okay? So counting this as the first one, okay? And so whatever M is, that's the first one. And so I'll make a little list over here. So M is the first one. The next fringe would be M plus 1. And the next fringe would be M plus 2. And the next fringe would be M plus 3. Okay? So this is the first one, the second one, the third one, the fourth one. And you can see that if I go all the way down to the 14th fringe, my index n keeps going up and eventually gets to M plus 13. So I'm going to write this as M plus 13 plus the extra half is 589 nanometers. Okay. And the reason I did all that is because, again, I might be curious just how much did this glass slide rise for that 1 centimeter? Now, ultimately, we want to know how much does it rise for 10 centimeters. So, excuse me, if I can just figure out how much it went up for the 1 centimeter, I'll just multiply by 10. Okay? And so let me subtract, calling this one minus that one. So 2T2 minus 2T1 equals, and I'll subtract that from that. So M minus M goes away. 13 minus, and there's really nothing to compare, is 13. And a half minus a half goes away. And so I'm going to say that. Now, if I factor out the 2, I will get what I'm looking for here. And that is that this increased by 13 half wavelengths. I'll bring the 2 over here. So T2 minus T1 equals. So grabbing my calculator, 13 divided by 2, 6.5, times 589 nanometers means we're looking at 3,828.5 nanometers is how much the thickness has increased as this little wedge shape. And of course, if you imagine doing that 10 times, the total difference, so D, the total thickness of the piece of paper, would be 10 times my T2 minus T1, or 38,295 nanometers, and probably best written as 38 point, I'll just round that to a 3 micrometers. And we could write that in millimeters, but I'll call that good. All right. I hope that was helpful. Take care.